Hello everyone, I am Zi Mingyi from Beihang University. Our work is Scene Context-Aware Indoor Object Selection and Movement in VR. In this paper, we present new indoor object selection and movement approaches by taking into account scene contexts. First of all, we will introduce the background from two aspects. Firstly, interaction techniques in VR are commonly separated into two types: contact-based selection and raycasting-based selection. The raycasting-based selection allows the user to select a distant object by just pointing to but not walking to it. So we choose three primary raycasting-based selection techniques as the baselines for our work. Controller-based technique has been widely used in commodity VR handheld devices. Head pose-based and eye gaze-based technique are developing very fast and can be treated as promising complements. Compared with eye gaze-based technique, head pose-based technique is easier to learn and more stable. Eye gaze-based technique is faster with better mobility, while its learning curve is steeper and it requires a higher workload. In our work, we evaluate the presented approach in all three selection modes to demonstrate its effectiveness. Secondly, our research are in virtual indoor scenes. Different from traditional 3D virtual scenes, indoor scenes usually exhibit fruitful contextual information provided by the constituent objects. And there are lots of excellent related work in using indoor semantic information and interior design guidelines. Automatic layout synthesis is easy to accomplish. For example, furniture layout and indoor scene synthesis could be realized based on priors associated with ergonomic factors. In addition to layout synthesis, the relationship between objects could be used to select and manipulate multiple object groups. According to related work, traditional raycasting techniques perform bad in some challenging conditions. We want to improve them with the following indoor scene contexts: object category, dependence relationship, group relationship and spatial relationship. Object category and spatial relationship are the most basic semantic information. When an object in one category depends on object in another category to realize its functionality, we say there is dependence relationship between them. And when objects of the same category that are placed closely, we think there is group relationship among them. Later we will explain in detail how to use these semantic information to improve traditional interaction methods in experiment. To improve the performance of raycasting techniques with sense contexts, we map the semantic relationships to keys of controller. Users can use the improved techniques by pressing simple combinations of the keys. How do the improved techniques perform in those challenging cases? Partially occluded objects may be blocked by their father objects due to dependence relationship. So when user was selecting target as parent object, he could select the target by pressing the menu button. For example, if the target is a nightstand, one can firstly select a bed, then switch to the nearest nightstand following the dependence relationship. In dense environment, it is difficult to select the target accurately. With the help of group relationship, users need to make precise selection. For example, there are many decorations on the bookshelf. The user was selecting the neighboring objects of the target by mistake, but he could easily switch to target in the same group by using touchpad. It is difficult to adjust orientation when moving objects using traditional 3DOF methods. We automatically adjust the yaw of an object during its movement. The movement objects always loot it at as parent object by dependence relationship within a certain distance. Of course, for specific objects, if the user does not want to place them according to the habitual angle, they can also place them manually. Our aim is to allow the user to focus on accurate placement rather than tedious adjustment of the object orientation. Another one is finding a suitable landing place. When selecting an occluded position, the raycasting technique will always point to the first object that is intersected with the ray. So we allow the ray to penetrate all supportive objects for finding the legal point to support movement object. For example, chairs are not usually placed on the table. We will penetrate the table along the rays to find a more suitable place for the chair. To explore the effect of improved methods in challenging cases and the user experience of the improved methods, we designed the selection experiment and movement experiment. Before formal tests, the participant practiced each method in a simple training scene. In formal task, the target object for selection was highlighted using a blue contour. The participant was asked to successfully select the correct object unless exceeding a 30-second time limit. Although the raycasting techniques allows the user to select a distant object, it is not easy to select occluded objects and dense objects. So we chose 5 representative conditions of indoor objects for evaluating the effect of the improved method. We recruited 12 participants from a university in this study. During the experiment, we recorded the selection time. After the experiment, the participant was asked to rank the methods based on his overall preference. In the end, we conducted a short interview to receive feedback on the overall experiment. The experimental results showed that the improved methods generally performed better than the original ones. For partially occluded objects and partially occluded object in dense environment, the improved methods performed better by having the selection time. The NASA TLX and UEQS results also showed similar statistics. In summary, Controller Plus had the lowest selection time. The refinements were better than the baselines when dealing with occluded objects or objects with distractive surroundings. In movement study, objects highlighted with yellow silhouette indicate the target object for moving, and green circles with an arrow indicate its target position. The participant selects object and moves it to target position by using movement methods. To focus on the movement test and facilitate user interaction, the movement methods do not require any extra operation from the user. Also, the user does not need to laboriously fine-tune object movement, especially when the target position is occluded by other objects in the scene. This is because the position and orientation of the object are already pre-computed based on scene contexts when applicable. We chose 3 experimental variables to evaluate indoor object movement, and we prepared 2 scenarios for each condition. Similar to Experiment 1, in the formal tests, the participant practiced each technique with different parameter settings in random order. During the experiment, we recorded the time for movement from the participant. After the experiment, the participant was asked to complete a subjective questionnaire and attend a short interview. The movement time results showed that by taking into account scene contexts, users can focus on selecting an object and moving it to the target position without tedious fine-tuning on object location and orientation. In general, it showed that Controller Plus and Head Pose Plus are more stable than Eye Gaze Plus in movement study. As shown in questionnaires, most participants felt tired with Head Pose Plus, and their thought Eye Gaze Plus was disappointing in moving objects to target position that was occluded, with large angle, and with long distance. The feedback on Controller Plus was moderate in all aspects. The selection and movement studies showed that the refined methods with scene contexts generally performed well. We further implemented a furniture rearrangement application based on the selection and movement interactions, as a preliminary demonstration of our approach. Compared to the user studies, the application reflected the performance of tested methods in a more complex scenario. In this VR application, a set of furniture objects were initially placed outside a virtual room. The task for the user was to select and move each furniture object into the room sequentially, following the target layout that was displayed as a picture on the wall. We conducted a small-scale user experience experiment with 3 participants. Each participant was initiated with his location outside the room. The task was to select, move and rearrange the furniture object as fast as possible. The average time for completing the furniture rearrangement task using Controller Plus, Head Pose Plus and Eye Gaze Plus was 94.5 seconds, 127.4 seconds and 91.8 seconds. Participants overall preferred Controller Plus most, because using the controller, they were able to select and move the target object more flexibly and frequently in the overall application about selection and movement. Our work has some limitations. Firstly, we only used controller buttons to access the scene contexts. Notwithstanding it was a natural way to blend context with traditional selection methods, other approaches can be further investigated. Secondly, in our experiment, only typical contexts of indoor scenes were used in our selection and movement tasks. For a totally new scene with an unfamiliar context, the user may need time to learn how to use the scene context. Third, we acknowledge that scene context was not fully exploited. Some more global contextual information can be further explored in the future. The selection study showed that Controller Plus and Eye Gaze Plus generally performed better than the other methods. The movement study showed that Controller Plus performed best in general. We believe that scene context will benefit human-object interaction not only for raycasting techniques, but also for gesture and haptics-based methods in the future. As shown in application, Controller Plus was more stable in the overall performance, with higher user preference. In summary, scene contexts are confirmed to be effective in reducing the interaction time, especially in complex interaction tasks with occluded object and dense environment. Thank you for watching the video.